Oh, hello, my friends, and welcome back to GSC 109 and the accompanying lab 109L. So I want to show you something. Come a little bit closer. Let's take a look at this specimen that I collected out in the field. It's a dark stone. It's rough to the texture. It's got a little bit of a metallic sheen to it. But this stone is actually a mineral. And it's called magnetite, a naturally occurring iron oxide that exhibits a very strong property that we use in GSC 110, General Physical Science 2, where we learn about rocks and minerals. And this property is distinct for specimens of magnetite. Do you want to guess what it is? Well, let's test it. Right here, I have a magnet. And when we make magnets, we actually use magnetite along with other alloys. And let's put it on. You notice on how the magnet sticks to the piece of magnetite. And that is what we want to learn as the phenomena for this week's module is what is the role of magnetism on our planet? And how can we use concepts found in the world of physics to be able to explain it as part of our learning journey here in this online course. But when we take a look at magnetite, we have a really good understanding on both a geological level, but also a physical science level. And when we take a look at it, magnetite forms through igneous process. It forms through the cooling of magma or lava. And as the molten rock cools, iron ions combine with oxygen to create an iron oxide. And that's very important because when we take a look at the magnetic property of magnetite, the magnetism of magnetite comes from its crystalline structure and the presence of both ferrous and ferric ions arranged in a very specific way. Magnetite is classified as a ferromagnet, meaning that it has regions called magnetic domains, also referred to as poles. And these are where the magnetic moments or the spin of electrons align to the net magnetic field. And again, this happens all within the crystalline structure. You see, when we look at the atomic level of the piece of magnetite, we can find that the iron the different ions are actually arranged in very specific patterns, with some having a canceling out effect, whereas the others will actually have an increased net magnetization. And that's where it gains this strong property. And then we call this natural magnetization, where a magnetite becomes magnetized as it forms, particularly as it's cooling down. We call this the Curie point. And as it's cooling down, it's gaining this property, and we call this thermoremnant magnetization. And because it's essentially locking in a magnetic signal that aligns with the Earth's magnetic field, as seen in this demonstration, where I'm taking the same magnet you just saw and allowing the poles, the pieces of graphite, which are the little shards in the plastic, to also respond or resonate to the magnetic field found in the magnet and align themselves to the poles. So think of it as the top of the plastic piece being the North Pole and the South Pole being the bottom of that plastic case. And the sides are more weaker magnetic signals. So in summary, magnetite forms through a variety of geological processes, mostly igneous, and it gets its magnetism from its unique structure, and where the iron ions create a net magnetic field, and it becomes enhanced through interactions of our own planet during its formation. Magnetism, and that sample of magnetite, play a crucial role in helping scientists answer various questions and understand the phenomena across different fields of study. I don't know about you, but being able to understand this topic helps me in my better understanding of different phenomena that are outside of the world of physical science. And there are some key examples that I'd like to share with you as part of this weekly welcome. First, we can take a look in the world of earth science. And being able to understand magnetism helps us be able to learn more about, say, plate tectonics. Our continents ride upon tectonic plates that drift around the planet, and being able to take a look at the magnetite that's being recorded in the different layers of our continents and how the Earth's magnetic field was at the time of their formation can help us answer big questions. By studying that orientation of magnetic minerals found in the rocks, such as magnetite, we can reconstruct the past positions of those tectonic plates. And this provides evidence for scientific theories, such as the continental drift theory proposed by Alfred Wegener. And it helps map the movement of the continents over millions of years. We can use it also for exploration. Magnetite is often associated with economically important mineral deposits, such as those containing iron, copper, and even gold. Magnetic surveys using remote sensing, such as satellites, will help detect variations in the Earth's magnetic field caused by underground concentrations of metallic materials. And this helps us locate very important ore deposits. We can also go and take a look at geomagnetic reversals. Earth's magnetic field periodically reverses, flipping the north and south magnetic poles as the rocks are forming will preserve a snapshot of that change. And by examining these records, we can understand how the history of Earth's magnetic field and frequency of these reversals plays out in the behavior of geologic time and may actually have has also maybe changed how Earth's history may have played out. And these are called magnetic anomalies. And these are just variations of magnetism in the rock due to different amounts of these concentrations of magnetic materials. These anomalies are used to map subsurface structures and will aid us in better learning more about our dynamic planet, especially around, say, volcanic regions, where we can actually see the rapid formation of these and deposition of these metallic materials. In the world of environmental science and climate change, magnets and magnetism and even magnetite play a crucial role here too. We can take a look at the magnetism in sediments, as layers of magnetite-rich sediments can be used to track past environmental changes, including sea level rise, glacial advances, and even retreats. Magnetite, if it's found in, say, oceanic rock units, report variations of the Earth's magnetic field because they're easier to collect and don't recycle as often as they would on the surface. We can also track pollution because magnetite particles can accumulate in the environment from industrial pollution, metals that we're producing, especially in sources like vehicles and local power plants. Environmental scientists can use magnetic measurements to track the movement of pollution around our planet, especially in also urban environments where there's factories that will take these properties or these materials and use them as a form of exhaust. And then once it gets caught in the air, travels around our planet. For those that are interested in biology, did you know that some animals actually use the Earth's magnetic fields as a way to travel and migrate? Many animals, such as migratory birds, sea turtles, and even some insects, use the magnetic field for navigation. And being able to understand how and visualize how these magnetic fields work can help us answer the big question about animal behavior. Organisms, such as bacteria, can actually incorporate magnetism into their bodies. and produce tiny magnetic crystals within their cells to help them also navigate. Studying these organisms, again, provides insight onto some of the earliest forms of life on our planet, but also how does bioengineering and nanotechnology truly play out as a phenomena. And those that are interested in space, well, we can take a look at planetary magnetic fields and solar activity and what is maybe occurring in deep space if we can pick up that magnetic signature. In summary, magnetism and all the way linking back to that sample of magnetite I just showed you will help answer a wide array of questions in fields found in geology, environmental science, biology, and even astronomy. And it helps lead us into the discussion of exploration and learning more about our dynamic planet over long periods of time, but also how do we use it in technology? And then be able to use physical science phenomena and concepts to be able to build that linkage between the natural world and that of the physical world. For a physical science class, we need to be able to approach this week's module through the contextualization of the different concepts you will be encountering. Because learning about magnetism and even our sample of magnetite offers numerous opportunities to be able to explore these fundamental principles and apply them. For an example, we learned that magnetite is a ferromagnetic material. It's a natural example of it, and it means it can be magnetized. It can retain its magnetism, and being able to study minerals such as this can help you better understand the behavior of what we call magnetic domains. But what is a magnetic domain? Well, there are specific aspects of different types of physics, physical properties that are very theoretical, and magnetism is one of them. We have gravity, Newton and gravity, and along with Kepler and many of the other astronomy-based physics, along with those that are also related to movement. But when we take a look at gravity, we also have its sister domain, and that would also be magnetism. And learning about magnetic domains helps explain how the atomic magnetic moments are aligned. When an external magnetic field is applied, these domains enhance magnetization and provide a concrete example of how these materials truly work and behave. And that's a great context to think about in the scope of the class, because we can also then build upon that. We can visualize magnetic fields and field lines for further study to be able to measure different types of variables when dealing with a problem focused on magnets. For example, we can sprinkle iron fillings around a magnet and using either a piece of magnetite, because they can be formed into magnets, we can observe the field lines being generated by the magnet and demonstrate the relationship between a conceptual model and a physical one. And then we can also assume that because of our Earth being a giant dipole magnet, the natural tendency of that magnet is also aligned with the poles of our planet and provides further insight to much more complex phenomena that understanding magnetism encompasses. For example, we can also look at electromagnetism, and that's going to be the big concept this week, because even magnetite can relate to it, because again, it can help form magnets. And electromagnetic induction is a very important concept because the magnetic properties can be used to demonstrate things like Faraday's law of induction, which states that a changing magnetic field will induce an electrical current. So it built scaffolds off of our previous weeks of study. And that magnetic field will produce an electrical current in a conductor. And we can experiment that in lab. And you can also compare magnetite to other materials being produced by our dynamic blue planets to be able that respond to different magnetic fields. And this can lead to further discussions on what materials truly make the best magnets. And going back to our relationship with electromagnetism, is that magnetism and energy go hand in hand because we use a concept called the Lorentz force. And by using a magnetic field, we can understand the effects of that Lorentz force, where a charged particle moving through a magnet experiences some degree of force. And this can lead to experiments, such as involving a current carrying wire, and again, a solenoid, to be able to produce that electrical current. Will allow us to also bring forth discussions such as electromagnetic waves and how light propagates to our planet, such as this aurora borealis that you see right behind me. We also see that we can also relate it to the potential energy and forces because there's actually a force between two magnets. Go ahead, try it. Find two magnets and try to get them to stick together or push each other away because we can even measure that force. And for those that might like to have a more mechanical application and technology, is that magnets are used in a variety of different technologies, such as motors and generators. Magnets' properties can be used to explore how fields are utilized in an electric motor and generator that helps power our homes. You can build a simple motor or generator and see how that magnet can convert electrical energy into useful working mechanical energy and vice versa. And this can deepen your understanding of the practical applications of electromagnetism and even magnetic levitation, where objects can be lifted by using magnets. For those that might like medical applications, medical physics is a true field that is just emerging because being able to use magnetism and the nanoparticles, you can apply those to use in a MRI, which is the module. If you have any questions about this week's lesson, feel free to reach out to me during my open office hours. You can send me a video chat request, an email, or swing by my office. And let's have an excellent day here on planet Earth, where the magnetic field truly aligns to your learning outcomes.